And we're live. Okay, no announcements, and it's with great pleasure again that I introduce Thibaut Benjamin, who will speak about globular weak omega categories as models of a type theory.
Okay, thank you. So yeah, I will speak about the joint work with Samuel Mimram and Eric Finster. And this work is about a type theory that is called CAT. So I'll just give you a brief introduction of what it is. So it's a type theory that was introduced by Finster and Mimram. And it's a type theory that is designed to describe weak omega categories. So for this talk, you can just think of weak omega categories as directed omega groupoids if you don't really know what it is. Or maybe you can picture them as the structure you would get if you were to have a hypothetical directed version of HoTT with directed identities or rewritings instead of normal identities. So something I want to emphasize is that it's a type theory, and it's not really a work inside of HoTT, or it's not really a work about HoTT. It's like a parallel type theory from HoTT, but also it's simpler than HoTT in many ways. It has less constructors, and they are easier to understand. And it's inspired by a work of Brunnery, who designed the type theory for describing weak omega groupoids. So he could describe the identity types of HoTT, the structure of the identity types of HoTT. And since it aims at proving the coherences of weak omega categories, you cannot, for instance, say, take this omega category and prove something about it. But you can instead state something like, for any weak omega categories with this and this and this cells, then I can compose it in such way to get this result. So contrary to HoTT, where you have weak omega groupoids just as types, you say, well, I have a type and this is a weak omega groupoids and I'll work with it. Here you can only say what the identity types of a type, how they behave, but you cannot manipulate them, really. So why are we interested in weak omega categories? Well, because they are very complicated. There are a lot of definitions for them, and not all of them are known to be equivalent. And they provide, mostly because they provide interesting steps toward directed HoTT, for instance. So the theory CAT is based on a definition of weak omega categories, which is due to Malsinotis, and he relies on ideas of Grothendieck. And the sort of big picture is this one. So you have Grothendieck, who defined weak omega groupoids in a way, and then Brunnery has given a type theoretic version of that. So he has translated this definition into a type theory. And in the other way, Malsinotis has added some directionality to this and to get weak omega categories. And you can think of CAT as sort of the push out of these two. So either it's like Malsinotis weak omega categories translated into a type theory, or it's Brunnery's type theory to which you add some directionality. And so my aim today is to present a bit CAT and weak omega categories very through the lens of CAT, so that you get some intuition for it, and then establish a formal relation between those two. And I'm following the paper that we have written and which is available here on arXiv. And especially for today, I won't really go into the semantics of the theory CAT because it's really complicated, but I'll study a much simpler case, which is a theory for a globular set, and I'll study the semantics in the good way. I'll present you the good way of studying semantics. I'll present you the bad way of doing it, and then the good way of doing it. And the good way of doing it being the way that generalizes well to CAT, for instance, or to other type theories. So first, I'll give you a few examples in CAT, and to understand what it's about, I'll show you, for instance, something that you can write in this language. So here you have first this co here, which is just a keyword release, it's just to say that we're declaring something. Then you have comp, which is the name of the thing that we are declaring, so that we can refer to it later. And then you have a huge pack of arguments. And you can really read them as a diagram. So here you have x of type star, and I'll just draw a point x instead, and y of type star, I'll draw a point y. And then you have f of type x to y, and I'll draw this as an arrow from x to y. So it's sort of, here it looks like a graph, but these are more general diagrams that you can describe like this. And then you have a result type. And if you read this, you see that it's something that takes as input a diagram like this and outputs an arrow from x to z, which is the source of the original diagram to the target of the original diagram. And so that's the morphism composition in weak omega categories. But if you were to look at these as identity types, then it would be the transitivity of identities. Or if you want directed identities, it would be transitivity of directed identities, or transitivity or rewriting. So another example is the identity, which in HoTT is more like the reflexivity of the identity. So here the reflexivity of the directed identity. And it says that for any x, which is just an object, you have an arrow from x to x. And I'll give you some more advanced examples, and that will be everything that you need to understand about weak omega categories and about the theory cat to follow this, what comes next. So, for instance, you have the unit. The unit takes as argument something like this. So it's an object x, an object y, and an arrow from x to y. And it says that if you were to compose the identity of x with f, then you get something that is just f. So, or maybe something that rewrites to f. And diagrammatically, you could look at it like this. So you have also, of course, a unit on the other side. And I'll introduce also the vertical composition. That's a very good example because it shows some of the divergence that you can have with respect to HoTT. So this is a bit tricky to read. So I'll just give you a diagrammatic representation. And it says basically whenever you have a two cell from F to G and another two cell from G to H, then you get a two cell from F to H. And if you were to do this in HoTT, that would just be the normal composition. But instead of having the type, which is an arbitrary type, it would be the base type would be a identity type itself. So it's just stacking up the identity types. But here you cannot really do that automatically. Things don't stack up this way. So if you want to describe the behavior, you have to go through defining a new thing, which is the vertical composition of two cells. Another nice example is what's called the whiskering. So again, again with some diagram, it says that whenever you have something like this, a configuration like this, you can get a two cell from the composition of F and G to the composition of F prime and G. And what this really tells you is that somehow the composition is functorial. Or in another way, it says that if you have a way to rewrite F into F prime, then you are allowed to rewrite F into F prime inside the term comp FG, if that makes sense. And that's exactly the same for the other variable of the composition. And I want also to show you the exchange rule because it's a nice intuition builder for weak omega categories. And it's a huge term here, and it represents this. So what is this? You have two cells here, a way to write F into F prime and a way to write G into G prime. And from this, you can go from the composition of F and G to the composition of F prime and G prime in two ways. First way is that you first rewrite F and then you rewrite G, or you first write G and then you write F. And these three cells here witnesses that these two ways should be related. Okay, so that's usual stuff in weak omega categories, and I don't want to go too much into this theory, but I want to stop here and provide you this kind of intuition if you haven't seen it before, and also to explain to you like these huge things of code, these chunks of code, how you can read them as diagrams. And that's going to be useful for what we're going to do now. So now I'm going to present you a much simpler theory, but I'll do it in a more formal way. And I'll present the notion of models that I'm interested in. So the theory that I'm interested in is the theory for globular sets. So globular sets, you probably know what it is if you know weak omega groupoids. And these are generalization of graphs where you can have arrows in every dimension, but the arrows needs to be between two parallel arrows. And you can see them as presheaf over base categories, the same way you can see simplicial sets as presheaf over base category. And the theory that I want to present, I call it GSETT, and it describes the globular sets. And it has two type constructors, but it doesn't have any term constructors. So that's why it's very easy to understand. The only term that I'm allowed to express in this theory are the variables. So the two type constructors are the following one. You have the type star, which will represent the objects of a globular set. And you have this introduction rule, which says that whenever gamma is a valid context, then you are allowed to introduce the type star as a valid type in the context gamma. And you have this arrow type here, which takes three arguments, t, u, and a. And the introduction rule here states that whenever t is a term of type A and u is also a term of type A, then you are allowed to build up the arrow from t to u over type A. And I want to convince you that using this, you can describe cells of a globular set. So we can just read directly from a context. So from a context, we can define a globular set, which are called V gamma. V it stands for variables. And we can just read directly from the context how to do this. So it's just like before. X is of type star, so I'll draw X as an object. Y is of star, I'll draw Y as an object. Then F is from X to Y, I'll draw it as an arrow here on my diagram. Same for G, H, K. A is from F to G, then I'll draw A as a 2 cell from F to G. So note that I forgot to write the type here as a subscript, but we can infer it, so it's not really a big deal. And what's more is that the substitutions also define morphisms of globular sets. So if I have a substitution from delta to gamma, it defines me morphism V of small gamma from V gamma to V delta. So really what I'm doing here is I'm defining a functor from the syntactic category. So it's the category where I take the objects to be the context of the theory and the morphisms to be the substitutions. And it goes from the syntactic category to the opposite of the category of finite globular set. Why is it opposite? Because you can see here that I go from gamma to delta to gamma, then the V goes from V gamma to V delta. And it's finite because the contexts in the theory are only allowed to be finite. I can't have infinite contexts. So I want to introduce you some special contexts in this theory that are called the disk and sphere contexts. And you can see that they really are analogous to the topological thing. I won't go into the details of how you introduce them formally as a list of variables and types, but they are really the same as the topological objects that you call the disk and spheres in the globular sets. And moreover, the disk have source and target substitutions. So for instance, the source substitution of the disk D2 here is the thing that maps so it goes from D2 to D1, and it maps the top, the arrow here of D1 into the top arrow of D2. And the target substitution goes from D2 to D1 again, and it maps this arrow here onto the bottom arrow. So these provide a functor from the opposite of G to the syntactic category of GSETT. And in fact, this functor, with the equivalence of category that was here before, sorry. So here I had a V, which is a functor from the syntactic category to the opposite of the finite globular set, which is an equivalence of category. And through this equivalence of category, this functor is just the Yoneda embedding up to an opposite somewhere. So this functor this is really useful to study what are called the models of the theory. And here I'll define the models in a way that might seem a bit strange at first, because it's not the usual way we define models. So I'll just remind you that the syntactic category is embedded with a structure of CWF. And if you don't really know what that is, just think of CWS. They really are the same. And I will define the models of the theory to be the morphisms of CWF from my syntactic category to set. And so why do I want to do this? Well, because if I were to look at a type theory as a set of rules, so as an axiomatic theory, then what I'm doing is I'm translating this axiom and incarnating them inside of set, and that's the logical notion of models. But we will see later that it relates in a nice way to the usual notion of models that we know. And we can prove that the models of the theory GSETT are equivalent to the globular sets. And that's really easy to do in a bad way. So what's the bad way to do it? Well, you said that the models are just the CWF morphism. And you recall that you have this D functor, which takes the disk object. And you have this equivalence of category and the Yoneda embedding such that everything commutes. And then you say, well, it turns out that being a CWF morphism is the same as preserving all finite limits. Well, these things has whole finite limits because it's the finite completion. And if you look at the models, so they are just the functor from the finite globular set, the opposite of the finite globular set to set, that preserve all finite limits. But this is the finite completion. So by definition, or by its universal property at least, these are the preshifts over G. But that's a really bad way of doing things. Why? Because I'm just separating the syntactic part and the categorical part. So here I'm using a huge hammer, like a huge categorical hammer, to say this is just the finite completion. And I'm first analyzing these to say the CWF morphisms are the same. I'm really separating those two things. And that doesn't work well for general categories. Especially we don't necessarily recognize the syntactic category as a finite completion of some sort. So instead, what I'll do now is I'll show you how to embed this CWF structure inside the universal property of the syntactic category. And that's what I want to call the semantic. So first thing is that the sphere context, they classify the types in the theory. So type is the same as a substitution to a sphere context. That might seem a bit weird, but it's very natural actually. So I'll just give you the last example here. So if you have G to F as an arrow in this complicated context, you can see it as a substitution towards the sphere of dimension 1 that associates X and Y to X and Y because F and G both go from X to Y, and that associates G being the source of this arrow and F being the target of this arrow. So since it's just a single arrow, you can just write it as a substitution from a single arrow to this one, and it really works pretty nicely. And as a result, the disk context classify the term of the theory. So substitution towards the disk context is the same as a term in the context. And now I want you to recall the functor that I am claiming to be an equivalence of category, and forget that it's an equivalence. and just reframe it. So remember that we said we were reading off the variables. So the variables are the same as the terms in this theory. It has only variables as terms. So the V gamma rewrites as the set of substitution from gamma to the image of something of the form D of something, right? And that's what is called the nerve functor associated to this D functor. And there is a very nice result which says that there is a natural isomorphism between the substitution from delta to gamma and the morphism of finite globular set from V gamma to V delta. And it might seem like a technical result, but from a type theoretic perspective, it's really, really nice. It says that a substitution is simply a way to every variable of gamma associate a variable of delta in a way that's compatible with the source and target relation, so compatible with the typing, really. So now I'll give you a more natural, maybe, notion of model. So a model of the theory GSETT, I want to see it as a CWF that supports the type star and arrow. And so that could express at least as much as the theory GSETT. And the nice thing is that I can give you a categorical way of saying this. So it should have a functor from the opposite category of G to C, such that the morphisms are sent into onto display maps, and the disk and sphere context that you can build in C from this morphism satisfy the same universal property. So I'm being a bit vague about it, but you can read it in the paper. It's really doable this way. And obviously, if you have a CWF morphism from the syntactic category to C, it induces a globular CWF. A globular CWF is this second notion of models. So I'm just changing the terminology here so that I can separate the two notions of models. So it induces a globular CWF on C simply by transporting the structure from the syntactic category to C. And now the key fact is an initiality theorem. So for this theory, I don't think it's really new, but the nice part is that it really generalizes well. And it says that the syntactic category is the initial globular CWF. And how would you do that? Well, remember that you have this functor here. You can just take the right Kane extension, and our equality between the substitution and the natural transformations between pre-sheaves shows that the extension exists, and the axioms of globular CWF ensure that it really makes this triangle commute, and it's a morphism of CWF. And so the corollary is that the models of the syntactic category are the same as the CWF structures on set. And now the CWF structures on set are equivalent to globular set. So this I'll not prove because there's no time, but it's really straightforward. There's no problem here. And this proof is the same as the bad proof, but it's the good proof. Why is it the good proof? Because first, it accounts for the CWF structure inside the universal property argument. And that's something that you can generalize well. And it's completely agnostic about the syntactic category. So you don't need to know what the syntactic category is. And about the requirements for being a morphism of CWF. You don't need to explicitly say it preserves this and this limits, so it is a morphism of CWF. And so that's the way to go if you want to generalize that to the semantics for the theory CAT. And so, well, for the theory CAT, we just use the exact same structure. So instead of having a globular CWF, we have CAT CWF. And we prove the initiality theorem, saying that the syntactic category is the initial CAT CWF. And as a consequence, the models of CAT CWF are equivalent to the models of CAT are equivalent to the CAT CWF structures on set. And these happen to be equivalent to weak omega categories. So I've glossed over all the details here, but this outline of a proof is very important, and I think it's a nice way of understanding a lot of different semantics of various type theories. So I think this outline would generalize to more complicated type theories. Maybe you could introduce some rewriting rules of computation rules. That's not fairly obvious because they come with added complexity. But we believe that's something that can be done, and it's a promising way of dealing with the semantics of type theories in general. Okay, so some reference, and thank you.
All right, thanks a lot. So I'll let everyone applaud in the way of their choosing. But yeah, this was great. So let's open the floor to questions. We have a couple of minutes. Maybe before we get to other questions, let's start with the obvious questions. You said you think it can be generalized to other type theories. So what do you have in mind?
Well, what I have in mind is using type theories as a framework for generalized algebraic theories, and for these, I believe you could get some mileage out of this global approach of encompassing like that. If you want to look at something with sigma types and pi types, I really don't know. It becomes fairly more involved, and I'm really not sure about what you could do about that. So for HoTT, really, I don't know if that's. I don't think that's a really practical way of getting something general. But understanding all the models of HoTT is expected to be something very hard. So it's not surprising that I'm not coming up with a way of doing it.
Yes, it is expected to be very hard. Okay. Any other questions? I'll just remind everyone that in order to ask a question, you need to go for the raise hand button, and I think then you'll be able to unmute yourself and turn on your video, and something will happen. Okay. Chaitanya?
Can you hear me?
Yeah.
Perfectly.
Oh, great. I was just wondering, have you thought about what a fibrant model of cat should be? Because for GSETT, it should probably just be a ready fibrant globular type, right?
Yes.
But for cat, it's a little trickier. Have you?
Yes. So I'm not so sure about what you mean when you say fibrant model.
A good notion of a model of cat, but in the, let's say, the syntactic category of homotopy type.
Oh, okay.
Or even in some category of fibrant objects or something like that.
Okay.
You can even take simplicial sets if you want.
I've not thought about that. Actually, I have not tried to study the semantics inside a type theoretic or higher setting. For now, I'm just focusing on more of a set theoretic approach. So I don't really know, and I think there's especially a very hard question here, in the fact that at some point you'd have to come up with a form of Segal condition, because cat itself generates morphisms. So I mean higher cells, and among these higher cells you have some of them which are invertible, and then you'd have the the
sorry, I'll interrupt you for just a
sorry.
second.
Yeah.
This room will be closing. So if you want to hear the rest of the answer, join the discussion room in the next 7 seconds. Otherwise, stay here, and in half an hour we resume.